Okay, good afternoon, everyone. I hope you enjoyed lunch. Welcome to the probabilistic programming session. I'm Firas Saad. I'm an assistant professor at Carnegie Mellon University, and I'm hosting the session today. So we will have a nice lineup of speakers. We'd ask to keep the questions mainly for the end, except for any quick clarification questions. Okay. So our first speaker is Haley from Aarhus University. They are presenting their work on Foxtrot, which is a separation logic for verifying properties of probabilistic concurrent programs. Take it away.
Testing. Well, first of all, congratulations, you're halfway through PLDI. So we'll celebrate this by starting off with a puzzle. And this puzzle, I will give you an example program, which I call two threads. At the very beginning, we use the parallel composition operator. So we have two threads running at the same time. And each thread samples a random number. It samples a number using the primitive rand. And rand n, in our operational semantics, samples a number uniformly from 0 to n with probability 1 over n plus 1 each. So in other words, rand 1 is just a fair coin toss that returns either 0 or 1 with 1/2 probability each. That gives us two numbers, x and y, and we return x times 2 plus y. And my question for everyone here is, what exactly is the behavior when you call this function? To analyze this, what you can do is that you can enumerate all the possible values of what x and y is. And that gives you a table or so. And you can see that the final value, x times 2 plus y, actually is just all the numbers from 0 to 3. In other words, calling this program returns a number from 0 to 3 uniformly with 1/4 probability each. Another way of saying this is that the behavior of this program is actually the same as this simpler one that directly samples with rand 3 as a primitive. So now, if we want to show if these two programs behave the same, can we actually prove that they actually behave the same? To actually prove this, we have to actually define what it means by two programs behaving the same. And a good notion of that is contextual equivalence. Contextual equivalence, if we want to say that E1 is contextually equivalent to E2, what that means is that if you consider all possible well-typed contexts, which you can consider as like larger programs with a whole, and depending on whether you substitute E1 into the whole or E2, it doesn't matter. The observable behavior of CE1 or CE2 is exactly the same. In general, proving contextual equivalence is defined as the symmetric closure of contextual refinement, which is basically the same, except instead of equality, you have the subset relation. Now, proving contextual equivalence or refinement is pretty hard. One of the reasons is that we're quantifying over all possible contexts. In our case, for proving two threads, it's even more difficult because we have both randomization and concurrency in the implementation of two threads. Now, both of these features are useful. For example, you can use it to implement concurrent randomized algorithms or data structures, like the concurrent approximates Morse counter, or you can use it to model cryptographic protocols, like secure multi-party computation. But these two language features in combination is very hard to reason about. And formal methods for these programs are quite limited and not very expressive. In particular, to the best of our knowledge, there were no techniques that you can actually use to prove contextual refinement of concurrent probabilistic programs. To solve this issue, we introduce Foxtrot. So what on earth is the Foxtrot? Foxtrot is the first higher order separation logic for proving contextual refinement of concurrent probabilistic programs. It is a very expressive logic, and you can use it to reason about higher order programs or those that utilize higher order local state. We formalize Foxtrot in the ROC proof assistant on top of the iris separation logic framework. And despite its name, it has nothing to do with foxes, nothing to do with trots. The key weapon that Foxtrot utilizes to prove contextual refinement is a refinement judgment proposition that lives inside the logic, written as so. Intuitively, if you're able to prove this proposition, it means that E1 refines E2 at the type tau inside the logic. And we have a soundness theorem that says that if you are able to prove this refinement judgment inside the logic using inference rules, this implies that E1 contextually refines E2 at the meta logic. To construct this refinement judgment proposition, we started off with the iris-based logic, on top of which we built the Foxtrot model implemented using expressed as weakest preconditions. We then construct a binary logical relation using the model, and we use the logical relation finally to define the refinement judgment proposition. Now, this chain to derive the refinement judgment is not novel. It is quite standard, and it's used in previous logics like reloc, clutch, or proxies. But what I emphasize is novel is how we define the model of Foxtrot. And because we have both concurrency and probability in our language, this model is different from previous logic, which I'll explain a bit later. Because Foxtrot is built on top of the iris-based logic, we immediately inherit all the nice reasoning principles for reasoning about concurrency. For example, we have impredicative invariants and ghost resources. Foxtrot is also inspired by various logics for reasoning about probabilistic programs, and it supports a wide range of logical facilities for reasoning about probabilistic principles. For example, we have error credits from Aarhus and fragmented coupling from Aproxis. It should be emphasized that getting all this to work is not straightforward. This is because the model of Foxtrot is different from previous logics, and we have to prove a lot of these principles from scratch. In particular, some rules, for example, a whole class of rules which we call presampling on the right, is unsound in our logic, which we have a counterexample in our paper. Let us take a step back and have a revisit the example I presented at the beginning. Let's prove one direction of the refinement, and I also generalized the sampling from ran1 to some arbitrary n and m for both threads. The key idea of this proof is that we have to be able to relate the ran sampling on the left and the two random samplings that happen concurrently on the right program. To do so, Foxtrot introduces this rule that allows you to relate one ran on one side and two rans on the other. And you can see that in the goal of this rule, it exactly matches what we want. And under a coupling reasoning principle, it suffices to prove that if the two threads on the right sample some arbitrary n and m, you can assume that the left-hand side samples exactly small n times big M plus 1 plus small m. And if you continue to symbolically execute, especially the right-hand side program, you can show that these programs eventually returns the same number, and that concludes the refinement proof. Now, this is one direction of the refinement, and to prove the other direction, you use a similar reasoning principle, but in particular, you have to use presampling tapes, which was first introduced in the clutch logic. As another example, we considered a implementation of a sampling function in the lib-sodium library. Libsodium is a widely used and well-respected cryptographic library, and it has this function, and as you can see from the implementation, it is quite straightforward to see what it does. Okay, I lied. It's not that straightforward, and that's why it's useful to show contextual equivalence. And as you can see from the simpler program, this just does some simple bounds check, and if it passes, it returns a random number from 0 to n-1 uniformly. Now, this equivalence is harder to prove for various reasons. One of them, as you can see, is that the sampling on both sides are sampling from different domains. Another thing that's quite tricky is that on the left, you actually have recursion, but you don't have recursion on the right. And finally, our result is stronger than those in previous logics because our equivalence also holds in contexts that might utilize concurrency. And this gives us more guarantee that the implementation is thread safe. To prove this equivalence, you have to utilize fragmented couplings and error induction, both of which are logical facilities introduced in previous logics. Now that I've given you sampled a taste of what are the examples we can prove, I want to take a step back and talk a little bit about the details of the model of Foxtrot. And recall that the soundness theorem of Foxtrot says that if you can prove this refinement judgment in the logic, that would tell you that would imply contextual refinement in the meta logic. To even state this theorem, we have to be a bit more precise about the operational semantics of a concurrent probabilistic program. And because we have both probability and non-determinism induced by concurrency, our operational semantics are parameterized by scheduler. This scheduler is a device that helps us resolve all the non-determinism of the execution of a program. In particular, it decides which thread to step next. More precisely, the scheduler is a function that takes in its internal scheduler state and the current configuration and returns a distribution of the next scheduler state it updates to and a natural number representing the next thread to step next. Now, because our operational semantics now has to take into account schedulers, so does the model of Foxtrot, and we bake in the definition of schedulers internally into the model. Let me give you an intuition of how that works. And to do so, we will have to go back and consider logics for proving contextual refinement for concurrent languages. So we ignore probability for now and just consider contextual refinement for concurrent language. For example, the ReLoc logic. If we look at the adequacy proof of ReLoc, it says that if you're able to prove this Hoare triple, what this means is that if you unfold this weakest precondition, then for every single step execution for E1, you can find and construct a witness trace for the right-hand side program such that their endpoints are related. And then, by taking induction on the number of steps for the left-hand side program, you will get a number of traces on the right for E2, which you can then combine to produce one master trace. Then you can conclude that for every execution trace for E1, you can find an execution trace for the right that witnesses this refinement. Okay, so this is the case for concurrency. What if we just consider languages with just probability and no concurrency? Well, it's slightly different because now instead of a single line representing the trace, we now have probabilistic execution trees to take into account probabilistic sampling. And we considered that for every single probabilistic execution tree for E1, the the adequacy theorem says that you can actually find a possibly larger tree for E2 such that their endpoints are related. In particular, there's coupling between the leaves. And then at the end, when you take induction on the number of steps for the left-hand side program, you will get a number of execution trees on the right, which you can then piece together to show that for every tree on the left, it will refine some tree for the right. Now, finally, in Foxtrot, when we have both concurrency and probability, now we have to take into account schedulers. And we quantify over all possible schedulers, and we consider every single step probabilistic execution tree of that scheduler zeta. And the logic will show that you can construct a scheduler for the right-hand side such that the probabilistic execution tree induced by the scheduler witnesses this coupling. At the end, we will take induction on the number of steps for the scheduler on the left, which will give you a number of schedulers for the right, which you can then piece together to construct one master scheduler to show that for every scheduler on the left, there is another scheduler on the right such that it witnesses a refinement. And this concludes the proof. What is interesting is that to piece together these schedulers, we actually have to use the axiom of choice, which is both interesting and gross at the same time, depending who you ask. In conclusion, we introduced Foxtrot, which you can use to prove contextual refinement of concurrent probabilistic programs. And it is very expressive in the sense that it can be used to reason about programs that utilizes other challenging language features like higher order functions or local state. There are more interesting things in the paper that I encourage you to check out. For example, the detail of how the model is constructed and its proofs. And also we have quite a lot of other interesting examples to show that our logic actually scales to other interesting case studies. Finally, I want to end by saying that my advisor is currently recruiting interns and PhD students. So if this is the kind of topic that really excites you, feel free to catch me later after this talk. Thank you all.
Okay, thank you for the very nice talk. We have some time for questions. So please raise your hand.
Thanks, Ali. Great talk. I was wondering, your schedulers, are they allowed to depend on the computation history when they make their decisions?
Yes. So recall that the definition of the scheduler takes in a scheduler state and a configuration. So the scheduler state can be defined to actually record the whole execution trace.
Do you know whether it actually makes a difference if you say they're only allowed to depend on the, say, current state and not on the history?
That is quite difficult. That's an open research problem because you're now considering a smaller class of schedulers, and that is something we're looking into, where we're looking to see whether we can prove refinement of smaller classes or more interesting classes of schedulers. At the moment, our schedulers is quite general, so we're talking about all possible kind of schedulers, including those that record everything.
Cool. Great work. Thanks.
Thank you.
Thank you for the great talk. Thank you for the great talk, and we are also working on concurrent probabilistic protocols. So, do you think your language can now express something like consensus protocols? Because that would be the case, that would greatly simplify our work.
That is a question that I can't answer right now, but I'm happy to, we can discuss later.
Yeah, sure.
We
are working on something more complex.
I'll be interested to see, whether there's any particular features that you use that we cannot support.
Okay.
Thank you.
Yeah, we have time for another question.
Thanks for the fantastic talk. What about divergence?
So, as in the program does not terminate?
Yeah.
So we have the same reasoning principles as in previous logics. For example, in ReLog, if the left-hand side program does not terminate, then there's a refinement trivially. So that we inherit that same reasoning for our case. For example, we have a loop induction that you can reason about programs that might never terminate. Thank you.
Okay, great. Let's thank our speaker one last time. The next speaker, come up, please.